Hello, good morning. Any doubts if you have from previous classes? The last class I was talking about nuclear technology. I started my discussion about nuclear technology. I introduced basic concepts of atomic structure which you already have studied in your school days. I did not do anything new there. I talked about presence of nucleus, presence of protons, neutrons, electrons, basic concepts of atomic number or atomic mass, what does that mean? One of the key point I discussed in the last class, which you may not have studied as such in school days, that I mentioned that think of chemical reactions which happen around us. A lot of chemical reactions are happening naturally. Many of the chemical reactions we have in industrial setup, into a lab setup, which is responsible for so many various types of industries which we come across. And my point was that all of the chemical reactions, they essentially are rearrangement of atoms and molecules and rearrangement of electrons. Even though when atoms are rearranging, nucleus is also changing its place, but nothing is happening to nucleus per se. Nothing is happening inside nucleus, and nucleus is not participating at all in chemical reactions. And if a reaction is happening, remember reaction is also like an interaction. It is a force. We require some sort of interaction for a reaction to occur. And I mentioned that the interaction which is responsible for chemical reactions is electromagnetic interaction, nothing else. There is not any other single interaction which is responsible for chemical reactions. But then I mentioned that there are reactions which occur at nuclear scale also, and there are many reactions which occur at nuclear scale naturally, the same way chemical reactions happen naturally. But there are many nuclear reactions, decay reactions, which we can induce into a lab setup, into industrial setup, and we can utilize those reactions for our own benefits. And that is what nuclear technology is all about. And I mentioned that one of the most important application of nuclear technology is in energy production. But there are many more applications which we will discuss here. I will start with this topic. Just write down a few things here about nuclear technology. Nuclear technology essentially refers to nuclear technology essentially refers to use of atomic and subatomic processes, use of atomic and subatomic processes involving the nucleus of an atom, involving the nucleus of an atom. This includes nuclear reactions, nuclear decay. Decay is also a type of reaction, but a very specific type of change. Nuclear decay, release of energy, It has applications in many areas. Such as energy production, agriculture, medicine, industry, space, defense, among others. Agriculture, industry, space, defense, medicine, among others. Imagine a chemical reaction. Some reactants represented here by A plus B, some products represented here by C plus D. one of the most fundamental law we have studied is conservation of matter, haven't we? Like we cannot destroy matter. We cannot create matter. We can change its form from one form to another form. What does that essentially mean is that if I start with mass m, let's say, if this A and B or whatever number of reactants, whatever we have, if I start with mass m, then whatever products may be, the mass will be exactly same. That mass is going to be conserved. One more fundamental law of nature which we have studied is conservation of energy, where we talk about that how energy can change its form, but we cannot create or cannot destroy energy. Nothing has been created or destroyed after Big Bang, which happened about 13.7 billion years ago. All of the matter, all of the energy has been the same. But here is a catch now. So why Einstein is considered as one of the greatest scientists, along with Newton, two greatest minds which have ever lived. So Einstein is the other name. So Einstein is very popular for many theories. Two of the most popular theories he gave. One of the theory he gave was called special theory of relativity, and another theory he gave that is called general theory of relativity. I will briefly talk about these two theories, not in today's class, in some other class. But one of the consequences of special theory of relativity is that Einstein demonstrated that how this concept of mass and energy are not separate from each other. So till now we have thought of energy as various forms of energy. We have thought of kinetic energy or potential energy. सबसे fundamental यही दो form है. We have kinetic energy, something is in motion, and because of that it has energy. We have potential energy. Potential का मतलब होता है that it has the potential to gain that much of kinetic energy because of in a configuration, because of in a state. जैसे I am at some high altitude, I have high potential energy, which basically means that if I start falling down on the ground, then all of that potential energy can convert into kinetic energy. So it literally is the potential of kinetic energy which I have because of the fact that I am in some state of system, I am in some configuration. I pull string of a bow very hard, and the further I pull it back, the more that arrow is going to be fired with more and more velocity. So this particular configuration, the more I pull it, it acquires more and more potential energy. Again, potential means that this much energy it can gain. And of course, we have read about many other types of energy, but all of them are essentially some manifestation of kinetic and potential energy, chahe chemical energy ho, electrical energy ho, heat energy ho, whatever we have studied. All of that is essentially some type of kinetic energy or potential energy. So we have come across many forms of energy, and we have studied that we can convert one form of energy to another form of energy. But Einstein now says that mass is another form of energy. So we think of matter and energy as two separate things, but Einstein then says that they are not two separate things, they are manifestation of same thing. So when we talk about conservation of matter and conservation of energy, these are actually not two separate laws. It is only one law, and I can collectively call it conservation of mass energy. That the total amount of matter and total amount of energy, it remains same. And Einstein also developed a mathematical equation which is very popular. I'm very sure all of you must have seen it somewhere or have heard him. MC square is a great rapper, right? So E is equal to MC squared jo hai, that is one of the fundamental equations which establishes the relationship between mass and energy. A lot of people again misinterpret this equation. Just say if I make a statement that mass can be converted into energy. If I only make that statement, then it's not 100% accurate statement. The better statement will be that mass is a type of energy, and hence mass can be converted into energy, but vice versa is also possible. Energy can be converted into mass. If I have very intense energy, nothing, only energy, then I can make matter out of it. I can create particles out of it. So if mass is converted into energy, but vice versa is also true, energy is also converted into mass. So Einstein gave this very fundamental law we call special theory of relativity. One of the consequences of special theory of relativity is this very famous mass energy equivalence equation E is equal to mc squared. So what does that mean here is that now let's assume that this is not a chemical reaction, but it is a nuclear reaction, and this has mass m1 and this has mass m2. Then in chemical reaction, m1 and m2 will always be same. But in nuclear reaction, there is no guarantee. In nuclear reaction, that m2 can be less, In some cases it can be more also, but it can be less. And the mass difference hai, what happens to that mass difference? It simply has been released as energy. So if let's say M2 is less than M1, it means that this M1 minus M2, multiply that with C square, and this much amount of energy will be released into nuclear reactions. And C here is, by the way, speed of light, just in case there is no confusion. See here it's speed of light in vacuum, which is 3 into 10 to the power 8 meter per second. So even if I have very small amount of nuclear matter, if I can produce nuclear energy, then even with very small mass, I can produce a lot of energy. Just to give you some context, in today's class, I'm going to start with nuclear fission. We do nuclear fission in nuclear reactors. 1 inch of uranium-235 pellet, this much big of uranium-235 pellet, can produce energy more than 10,000 kg of coal. So the type of energy density we are talking about when we mention nuclear energy. So the starting point in this entire discussion is, give this heading, nuclear technology in energy production. Nuclear technology in energy production. Write down a line here. There are mainly two ways. There are mainly two ways to produce energy, to produce nuclear energy, nuclear fission, nuclear fusion. So let's start with nuclear fission. Give this heading, nuclear fission. There are many nuclei, don't write it right now. There are many nuclei which are not very stable. Some nuclei are much more stable, some other nuclei are not very stable. You can ask a question, why would that be? So the actual answer requires understanding of nuclear science, which we do not have to do. But I can intuitively explain that why some nuclei will be more unstable or some will be stable. The same way, how some elements are or how some atoms are more chemically reactive. There's a think of sodium. Sodium is very chemically reactive. When you throw sodium in water, you can literally see reaction happening. But at the same time, neon is not, argon is not. These are not chemically reactive. So the same way an atom can be stable and unstable, and it essentially depends upon the configuration of electron. You have studied that electronic configuration, आपने 9th 10th में सीखा होगा, that this electronic configuration which you learn to write. So the arrangement of electrons decide that how reactive an atom is, or how stable or unstable an atom is. Same way, the arrangement turns out that protons and neutrons are not just idle particles inside nucleus. Protons and neutrons have their own motion, they have their own configuration, they have their own way of arranging inside a nucleus. And some arrangements are stable, some other arrangements are not very stable. One of the most famous unstable nuclei is uranium-235. Uranium has atomic number of 92. It has atomic mass of, it has many isotopes. I'm talking about one specific isotope which has atomic mass of 235. This uranium-235 already is not very stable. We want to induce more instability to this uranium. How do we do that? We add extra neutrons inside this nucleus. So we literally start with a reaction which can produce neutrons, by the way. And neutrons, because neutrons are electrically neutral, neutrons का खुद का अपना charge है नहीं, so they will not be affected by either electrons nor protons, and they can enter inside nucleus. So they can enter inside atom, and then they can enter inside nucleus. And this entering of nucleus makes this nucleus, entering of neutron inside nucleus, make uranium much more unstable. and it disintegrates. It divides into lighter nuclei. One of the products can be barium and krypton. About 3 more neutrons will be released, and a lot of energy will be released. We do not have to memorize these reactions, except the fact that uranium undergoes disintegration. So I start with a heavy nucleus which is not very stable, and I caused more instability. It's like a person जो बहुत गुस्सा है और आप उसको taunt कर रहे हो. इंसान literally फट पड़ेगा, ऐसे समझ लो. So this is not a very stable nucleus, and you want to induce more instability here. And because of that, this uranium disintegrates and now converts into lighter nuclei of barium or krypton, which have much less atomic mass compared to uranium. One of the most interesting thing which happens in this reaction is that I started with 1 neutron, but on an average I can get 3 neutrons. On an average 2.7, so sometimes 2, but a lot of times 3. But I will get more neutrons from the amount I started with. A lot of energy will be produced, and that energy will be simply, it can easily be calculated, because if I take this mass m1 and I take this mass m2, then this m1 and m2 will not be equal to each other. The energy can be calculated as m1 minus m2 multiplied by c square. So this much amount of energy will be released. To appreciate this amount of energy, think of c square. C is 3 into 10 to the power 8. C square is 9 into 10 to the power 16. So 9 into 10 to the power 16 को अगर हम बहुत small mass से भी multiply करें, mass of let's say even 1 microgram, that amount of energy, that joule of energy is really, really huge. So even if that mass difference is very small, c square is such a large value that this energy is going to be very, very huge. That is the mechanism of nuclear fission reaction. So fission reaction essentially involves disintegration of a heavy nucleus into lighter nuclei. You can write it down. Nuclear fission involves bombarding an unstable nucleus such as you can write down example, such as uranium 235, U235, uranium 235. The nucleus becomes further unstable. The nucleus becomes further unstable and splits into 2 or more nuclei, splits into 2 or more lighter nuclei, 2 or more lighter nuclei, 2 or more lighter nuclei. A huge amount of energy is released. A huge amount of energy is released. A huge amount of energy is released, which can be calculated, a huge amount of energy is released, which can be calculated using Einstein's mass energy equivalence, using Einstein's mass energy equivalence relation, Einstein's mass energy equivalence relation. E is equal to mc squared. E is equal to mc squared. So there is a very specific thing I want to highlight. So the first thing, of course, I told you that the amount of energy will be very huge, even though that mass difference is very less. But let's talk about that. If I have some uranium sample, I have, let's say, 250 gram of uranium-235 sample. I will be arrested, by the way, for that. You cannot have that. But if I have uranium-235 sample of even 250 gram, how many number of nuclei will be there into that sample? I have a simple question, that how many number of nuclei will be there into this sample? 10 to the power what exactly? Avogadro number का concept पढ़ा आपने? 235 gram of uranium will have 10 to the power 23 multiplied by 6.01, something like that. So the number of atoms in a sample of 250 gram of uranium will be in the range of 10 to the power 23, trillions to trillions of numbers. I'm not talking about millions or billions, trillions of atoms, and every atom has nucleus inside it. This was a reaction involving just one nucleus. It did not involve many reactions. Now, one of the most interesting feature of fission reaction is that it produces more neutrons than consumes. It started with one neutron, but produced more neutron. Now, so I have to initiate this reaction. Nuclear fission is initiated. That we need to initiate this reaction, but after that you do not have to do anything. Because reaction in itself is producing neutrons, and those neutrons will go and carry on nuclear fission to other uranium nuclei in the sample. And remember, there is no dearth of uranium nuclei, even in a sample containing 250 gram of uranium. So I started with one neutron, which reacted with uranium-235, and that produced about 3 neutrons. And these 3 neutrons can go and react with 3 uranium-235 nuclei, and they can produce 9, and they can produce 27, and 81 and 243, you get the idea. This growth is called exponential growth, where things start increasing in geometric progression, and जो आपका growth है, जो change ratio जो है, that is more than 1. Whenever you have a growth like this, we call this exponential growth. And exponential growth is a very, very powerful tool, very powerful tool. To appreciate exponential growth, I can tell you a story. A person who introduced game of chess to a sultan. Sultan was very happy. He asked that whatever you want, I can give it to you. And he asked for a very simple thing, that I want 1 grain of rice on the first square, 2 on second, 2 to the power 2, 4 on third. You get the idea. So on the 64th square, he needs 2 to the power 63 rice grains. If you add all of that, it will come out to be 2 to the power 64 minus 1. Now 2 to the power 64 is such a huge value that cover entire earth with rice, 1 layer of rice, and you will not be able to fulfill it. So you may think 2 to the power 5 and 2 to the power 6, but the number keeps on increasing. Every next number in that series will be much, much more than the previous number. So exponential growth suddenly becomes very explosive. The number becomes so huge that it becomes unimaginable. I did not even have to go to 100, 2 to the power 100, 2 to the power 1000. Even 2 to the power 50 is a very huge number. So exponential growth is a very, very powerful tool. And when you allow this, and by the way, such reactions are called chain reactions, because I started the reaction, after that reaction continued itself. I did not do anything. It became a chain reaction, series of successive reactions once we initiated. If I do not stop this, then and by the way, every such reaction is producing energy. Remember, all of that reaction is producing that huge amount of energy we talked about. So in a very short span of time, such a huge amount of energy will be produced that it will vaporize the entire region wherever this reaction has been started. And that is what nuclear bombs are. When we think of nuclear bombs or atomic bombs, they essentially are nuclear fission reactions which have been allowed to grow uncontrolled manner. That we do not aim to control this reaction. We aim to produce as much as energy in as much as less time as possible. And that is what nuclear bombs are all about, essentially uncontrolled nuclear fission chain reaction. तो आप ये लिख सकते हो इसको? Nuclear fission often leads to a chain reaction often leads to a chain reaction. Chain reaction because more neutrons are produced. More neutrons are produced. More neutrons are produced if this reaction, if this chain reaction if this chain reaction occurs in an uncontrolled manner, huge amount of energy will be produced. Huge amount of energy will be produced. Huge amount of energy will be produced in a very small time. In a very small time. This is the mechanism. This is the mechanism used in atomic bombs. This is the mechanism used in atomic bombs. However, write down in next paragraph, however, if we absorb excess of neutrons, if we absorb excess of neutrons, in a controlled manner, if we absorb excess of neutrons in a controlled manner, then fission rate can be controlled. Fission rate can be controlled. And we can use the energy for electricity. We can use the energy for electricity. This is the mechanism. This is the mechanism. This is the mechanism of working of a nuclear reactor. This is the mechanism of working of nuclear reactor. Working of nuclear reactor. So this is what do I mean by when I use the word uncontrolled chain reaction and controlled chain reaction. The purpose of nuclear reactor is very simple, that we need to allow this reaction to go in a controlled manner. We do not want this excess of neutrons, but we do not also want the reaction to stop. We do want both of these things. We want this reaction to continue as long as we have fuel available, but we also do not want this rate of fission reaction to increase exponentially. That will lead to an explosion. We do not want that. We want to control it. So nuclear reactor का जो fundamental purpose ये है, that how can we produce energy in a controlled manner using nuclear fission. Now energy security is very important for any country's growth. Should be very clear. And India particularly is dependent upon lot of import, particularly in oil and natural gas. Think about it. हमारा जो import basket है उसमें जो सबसे बड़ा contribution है, the biggest contribution in import basket is oil and natural gas. So more and more nuclear energy production allows that India can become independent in energy production. But it's not that simple. There are a lot of complications, a lot of challenges. I will come to that part later. But give this heading, Nuclear reactors. Nuclear reactors. We already have talked about that nuclear reactor का जो purpose है to have a controlled chain reaction, controlled chain nuclear fission reaction to produce electricity. That is the purpose. Let's talk about some of the important parts and important components of the nuclear reactor. The first important component will be fissile material. Fissile material. Fissile material का मतलब है we are talking about those things which can undergo fission easily. The same way we think of certain type of fuel, for burning few things is easier compared to other things. Burning of coal is very easy, and because of that we can produce a lot of energy. So similarly, not everything can undergo fission exactly with the same efficiency. Few things can undergo fission much more easily compared to others. So आप लिख सकते हो in one line, nuclei which can undergo fission easily. Nuclei which can undergo fission easily. Nuclei which can undergo fission easily. For example, the most famous example all of us should remember is uranium's isotope with atomic mass of 235. We can simply write uranium 235. Even if you write it like this, it's totally fine. Then another isotope of uranium is uranium 233. That is also a very good fissile material. Then you have this another nucleus called plutonium. Plutonium has atomic number of 94, and one of the isotope of plutonium which has atomic mass of 239, that's also very good fissile material. So this is plutonium. U is uranium. The first thing, whenever we have to design a nuclear reactor, the first thing we have to explore that do we have these resources available? If not, then we have to perhaps buy it, import it. Turns out that import is much more restrictive in case of uranium or plutonium. The second thing, one of the most important component inside a nuclear reactor will be control rod. This particular part of the reactor is called core of the reactor. This is the fundamental core. Inside core, nuclear fission happens and energy is produced. And you'll find that you have this fuel rod here made of uranium, which we are going to use. But parallel to that, we are going to use control rods. So control rods are made of those materials which can absorb that excess of neutron. We know that why this reaction becomes uncontrolled, because it produces more neutrons than what it started with. So the goal of control rod here is that it should be able to absorb excess of neutrons so that this reaction can continue in a controlled fission manner. तो आप लिख सकते हो in control rod made from materials that absorb neutrons. Made from materials that can absorb neutrons. That can absorb neutrons. Example can be boron, cadmium. Lot of time you will come across this term that this reactor has become critical. And by the way, this term you'll witness much more often, because Government of India is very clear that we are going to have at least one nuclear reactor operational. We are constructing many reactors, and every year we want a new reactor to become operational. So nuclear energy पे हमारा बहुत सारा focus है. And this term that this reactor has become critical, you will come across this a lot. So critical here simply means that the number of neutrons which are being produced, they are enough that they can continue the reaction without letting it become uncontrolled. So that number comes out to be somewhere around 1.1, not exactly 1, it comes out to be 1.1. So ऐसे आप imagine करो that you have neutron plus uranium 235. All I need to do is that I need to keep absorbing excess of neutrons. So for example, I removed this neutron, I removed this neutron. So ये जो पूरा chain है, I have removed this entire chain. Similarly, here I have removed this neutron and this neutron. So I keep having this nuclear reaction in a controlled manner. So every reaction is producing one neutron, and it is then continuing this reaction further, where it can produce energy in a controlled manner. Ideally, the average number is 1.1, which basically means we do not have to remember that. Nobody is expecting you to memorize this. Why 1.1? Because not all neutrons will be used for fission. Some will be lost also here and there. And we do not want the reaction to stop. So we want a reaction to continue as long as we have fuel, but we also do not want that it becomes uncontrolled. Whenever we achieve a situation like this, we call that this reactor has become critical. This reactor has achieved criticality. So you'll come across this word, criticality of a nuclear reactor. आप ये लिख सकते हो? Criticality of a nuclear reactor signifies criticality of a nuclear reactor signifies criticality of a nuclear reactor signifies that fission can continue in a chained but controlled manner. Chained but controlled manner. The third major part here will be coolant. तो ये जो कोर है, you have nuclear fission happening here. And that nuclear fission will produce a lot of energy, but we need to keep removing that energy for obviously two reasons. The first is that we do not want that energy to build up inside the core. It is going to burst otherwise. So we want to stabilize the core. And of course, the most obvious reason here is that we need to keep removing this energy so that we can utilize this energy for production of electricity, and we can connect that with normal grid. So for that, we keep pumping cold water here. The water which we are going to pump inside the core, there will be pipes inside this core, will be cold water, but the water which will come out, that will be hot water. And we will use the energy of that hot water to heat up some fluid, some water, to produce steam. And we can use that steam to move a turbine. The turbine is connected to a generator, which can produce electricity. That part is same as what happens in coal-based thermal power plant. जो thermal power plant जहाँ पे हम कोयला जलाते हैं, वहाँ पे भी हम same काम करते हैं. That as we burn up coal, it produces a lot of thermal energy. We use that thermal energy to convert water into steam. We use that steam. Steam has a lot of pressure, a lot of energy. We use that steam to move a turbine, which is connected to a generator, which can produce electricity. So that part is exactly same. But in thermal power plant, the source of energy was burning of coal. In nuclear power plant, the source of energy is nuclear fission of uranium-235. So we have to keep supplying water here, cold water, in the core of reactor. But the water which will come out, that will be hot water, and we have to use that energy to produce electricity. So that is why water, or we can also use heavy water, by the way. So water is H2O, but I told you in the last class that hydrogen has an isotope, deuterium. Now here is the thing, your chemical properties are determined by number of electrons. It is not determined by number of protons or number of neutron. That in your shell, how many electrons are there? So hydrogen has one proton and one electron, but so has deuteron then. So deuterium hai, that also has one proton and one electron. It has one excess neutron, but neutron does not change your chemical property. Even tritium has one proton, one electron, but it has two neutrons, hence atomic mass becomes 3. But all three of them will exhibit similar chemical property, but different nuclear property. So that is why, if I can have H2O, I can also have D2O. So if water is there, and if deuterium is naturally found in the nature, then we can also find heavy water. And turns out that this assumption is actually 100% accurate. आप कोई भी natural water body चले जाओ, कोई river ले लो, ocean ले लो, lake ले लो, whatever natural water body you pick, on an average in every water body, you'll find that every 5,000 liter of normal water, you'll find 1 liter of heavy water. So heavy water का जो percentage है वो बहुत कम है, only 1 liter out of 5,000 liter, but it is there. And it is there in each and every natural water body. The best available for us is ocean itself. So you can utilize or you can recover that heavy water from water, and you can even use heavy water as your coolant. So आप लिख सकते हो, coolants are fluids. Coolants are fluids that removes heat from the reactor core, that removes heat from the reactor core, from the reactor core, and transports it to a generator to produce electricity. Transports it to a generator to produce electricity. Produce electricity. So coolants can be H2O, water. In some cases we can also use D2O. So H2O is water, D2O is heavy water. We call it heavy water because this deuterium, ये जो element है, it is nothing but one H2. So it has one proton, one electron, but now one neutron also, hence one H2. It can be a gas also. Lot of reactors. In India, we are not using any gas-cooled reactor, but in America, this is becoming actually quite popular, that you have gas-cooled reactors. Or it can also be a liquid metal. जैसे, even in India, we do use liquid sodium. All of these are candidates to make a coolant which can transport heat from the core so that we can use that heat energy to produce electricity. And one more component which we should know here is heavy water does not mean salty water. There is a question that does heavy water mean salty water? Not at all. Heavy water means we're talking about water which is made of deuterium, not hydrogen. So hydrogen is 1H1, but deuterium is 1H2. And turns out that deuterium is not as prevalent as hydrogen, but it is there. Deuterium is found in nature, and the same way hydrogen can react with oxygen and can form water, deuterium can react with oxygen and can form heavy water. So heavy water is not salty water. We are talking about water made of deuterium. These reactions are always running to store energy in the power grid. So nuclear reactor का एक बहुत बड़ा benefit ये है that you can have 24/7 supply of energy. One of the biggest challenge in renewable energy sources such as solar and wind, which are the two most popular source of energy, that if you do not have sun in the sky, you cannot produce solar energy. It's as simple as that. Coal-based power plant का एक फायदा है that I can burn coal anytime and can produce energy. And the same benefit also is with respect to nuclear power plant, that a power plant can run 24/7 and all the time it can produce energy. So that is one of the benefit of nuclear power. Anyways, moderator. मॉडरेटर का गोल है to slow down the speed of neutrons. Remember, every reaction is producing neutrons. We need to slow down that neutron. Why? Turns out slower neutrons have more probability that they can induce nuclear fission. So slower neutrons have higher chances of inducing nuclear fission reaction. And often we will find that moderators and coolants will be same. For example, both water and heavy water, they are very good moderators, but they are also very good coolants. आप लिख सकते हो? Moderator is used to slow down. Moderator is used to slow down. Moderator is used to slow down fast neutrons produced by fission. Fast neutrons produced by fission. Fission. Slower neutrons are better at causing 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 fission. And the best type of moderators, by the way, if I have to write down examples, again same, H2O and D2O. Not liquid sodium. Liquid sodium is not a moderator. But these two things, water and heavy water, they both are very good moderators also. They slow down the speed of neutrons. So these are some of the fundamental elements of course, nuclear reactors are much more complex than that. We are trying to understand the very basics of it, the basic science bit of nuclear reactor. So in a nuclear reactor, we can have controlled fission, we can produce energy. But nuclear reactor का खुद का design अलग-अलग हो सकता है. There can be many types of nuclear reactors, but I will only be talking about nuclear reactors which we use in India. The most famous type of nuclear reactor in India is called pressurized heavy water reactor. So give this heading, types of nuclear reactor. Pressurized heavy water reactor. This is one of the most famous types of reactor. Particularly for us, this is very important because most of our reactors are pressurized heavy water reactor. And pressurized heavy water reactor, we use heavy water as moderator and coolant. Heavy water के use करने के कुछ फायदे हैं compared to normal water. Heavy water can carry more amount of energy compared to water. That is the most fundamental benefit of pressurized heavy water reactor compared to pressurized water reactor. जैसे another type of reactor can be pressurized water reactor. And as the name suggests, we use water, not heavy water, but water, H2O. And then you have a type of reactor, which is a very popular design in US. And we have collaborated with US in one of our reactors, which is called boiling water reactor. So in India, we do have boiling water reactor. Same, H2O. as moderator and coolant. Moderator and coolant. So what is the difference between PWR and BWR then? Pressurized water reactor, if they both are using water as moderator and coolant. The fundamental difference is how they use water. And वो नाम से ही clear है. In pressurized water reactor, water is used at very high pressure. What does that mean? The water which is pumped inside the core of the reactor is at very high pressure. Turns out that boiling point or melting point which we have studied till now, they are not just dependent only upon temperature, they are also dependent upon pressure. I hope everybody knows about this, that at higher pressure, water ka jo boiling point hai, that is going to increase, at lower pressure it will decrease. So that is why inside a pressure cooker, where the air pressure is very high, the water boils at much above than 100 degrees Celsius, and your food can be cooked much more faster. Go to mountains, the water starts boiling at much lower than 100 degrees Celsius, because at mountains pressure, atmospheric pressure is less. So boiling point also depends upon atmospheric pressure. When we say that water boils at 100 degrees Celsius, then we are talking about normal atmospheric pressure. Normal atmospheric pressure is 1 atmospheric pressure. Pressure ka jo SI unit hai, that is Pascal. So that will be about 1.01 multiplied by 10 to the power 5 Pascal. So at 1 lakh Pascal, water boils at 100 degrees Celsius. But if it is more than 1 lakh Pascal or less than 1 lakh Pascal, accordingly water boiling point will increase or decrease. So that is the first thing all of us should be aware about, that water's boiling point will increase at higher pressure. So water which is pumped inside pressurized water reactor is pumped at high pressure, so that the water which comes out has lot of heat energy, but is not going to boil it. It is not going to be a boiling water. It does have lot of energy, but it is not steam now. It will not convert into steam. We have to allow this heavy water to release its energy to some other water, and we can use that water to convert into steam and move a turbine and produce electricity. But in boiling water reactor, the water which is pumped, that is done at normal atmospheric pressure. This water heats up in the core of reactor, but because it is at normal atmospheric pressure, the water which is going to come out, that will be boiling water, it will be steam, and we can directly use that steam to move a turbine and we can produce electricity. So both of these reactors have their own set of benefits and shortcomings. I will not go into nitty-gritties of that. But the fundamental difference between a pressurized water reactor and a boiling water reactor is how you are going to use water. In pressurized water reactor, at high pressure, hence the water which comes out is not going to convert into steam, even though it does have a lot of energy. In boiling water reactor, the water which will be pumped, that will be at normal atmospheric pressure. Hence the water which will come out of the core of the reactor, that will be converting, that will actually be steam. A lot of that water will be steam, and we can directly use that to produce electricity. In India, most of our reactors are pressurized heavy water reactors. So there we use heavy water, but again, very same as pressurized water reactor, heavy water is pumped at very high pressure. So this is about type of reactor. Another type of reactor which now has become even more important, it was always an important topic, but now it has become even more important. It's called fast breeder reactor. It's called fast breeder reactor. I'll be talking more about fast breeder reactor, not right now. Before I do that, I want to discuss one more topic. I want to discuss a small topic, but nonetheless important one. Give this heading uranium fuel cycle. Uranium fuel cycle. कोई भी फ्यूल जब हम यूज करते हैं, whatever fuel we use, let's say you're using coal as a fuel in thermal power plant. But that coal will undergo a lot of processes. The coal which you mine from coal mines, it will have a lot of dust, lot of ash. We need to clean it. A lot of times coal is cleaned before we can actually burn it up so that we can reduce the air pollution level of coal. So all the processes a particular fuel undergoes through after it has been recovered, it can be called fuel cycle. So even coal has its own fuel cycle. Petrol has its own fuel cycle. So the petroleum products which you have extracted from the earth's crust, we do not use that directly in our cars. It undergoes through various processes before it can become petrol or diesel or something else, and we can use that in our day-to-day life or for whatever purpose we are using. So similarly, that is also true for uranium. That uranium, when we extract from Earth's crust, now there is a thing, uranium is quite abundant in Earth's crust. Uranium is not a rare mineral. मतलब ऐसा नहीं uranium का कोई rarity. Uranium बहुत abundant है Earth के crust में. So when you extract uranium, it undergoes lot of processes, and collectively all of those processes, from the moment we extract uranium as part of mining, and finally how do we dispose of the nuclear waste, because the same way when you burn coal and whatever is left has become fly ash, rock, literally it becomes rock, and we need to dispose of that fly ash in an environment friendly manner. Similarly, when we use uranium, whatever is left inside the core of reactor, that is waste, but that waste is the most dangerous waste we know of, and we need to manage that waste really with utmost care. So all of the processes together we call nuclear fuel cycle. So I'm going to make a diagram here and I will be explaining all of that step one by one, but you make this diagram with me. Uranium fuel cycle starts with mining. Milling. There is a process conversion also. I'm going to skip it. I directly want to talk about enrichment. Fabrication. Nuclear fission at reactor. Interim storage. Spent fuel reprocessing. Final disposal. You can make an arrow like this also. From spent fuel reprocessing to enrichment. Write down a line before I can explain all of this. Nuclear fuel cycle involves all the processes starting from mining till final disposal of nuclear waste. Final disposal of nuclear waste. It involves following steps. It includes following steps. It includes following steps. First is mining. It includes following steps. First, mining. Mining is self-explanatory. I do not have to explain mining further. The only thing I want to talk about here is that when you are going to mine, you'll find uranium ore, not uranium. And uranium ore will have a lot of impurities. So we need to take care of that impurity, and that we do in milling. So second is milling. Milling. इसमें एक लाइन लिख लेना, uranium ore is crushed. Uranium ore is crushed. And using physical and chemical filtration methods. Using physical and chemical filtration methods. Natural uranium is recovered. Natural uranium is recovered. Physical and chemical separation methods, natural uranium is recovered. So the first was mining. Mining, say we got uranium ore. Uranium ore has a lot of impurities. We took care of those impurities in the milling process. There is a process called conversion also, where we convert that uranium into uranium hexafluoride. We do not have to go into this detail. I directly am going to jump to enrichment. Now enrichment is one of the most important step here out of this nuclear fuel cycle. Because the natural, I told you that uranium is not a rare mineral. Uranium ऐसे कोई नहीं है कि rare mineral. It is in abundance. The problem is, the uranium which is found in nature, or the natural uranium which we have recovered from nature, that natural uranium will comprise of two isotopes of uranium. It will comprise of uranium-238 and it will comprise of uranium-235. Now I gave you a list of fissile materials which can undergo fission easily, but I did not mention uranium-238 there because uranium-238 is not a good fissile material. So uranium-238 is not a fissile material. Uranium-235 is. It is found naturally. However, the sample which I have just recovered after milling, it has only about 0.7% of uranium-235 and it has more than 99%. 99.3% I have uranium-238. So even though uranium is not a rare mineral, uranium-235 is actually quite rare. Uranium-235 is not in abundance here. If I try to use this fuel, it will not be a very efficient fuel. So the purpose of enrichment process is that we aim to increase this concentration from 0.7% to up to 3, 4 or 5%. Very simple. So saying this is much easier, but doing this is much more difficult because remember here now we have to separate between isotopes. Separating between two things which are two different chemicals or two different elements, that's easier. That we can always do using, there are so many different ways, physical methods or chemical methods, that I have to separate between two things which are two different things. Now here we are talking about two same element but two different isotopes of the same element. So I have a sample, I have a mixture where I have two isotopes, and within those two isotopes I need to remove uranium-238 so that the concentration of 235 automatically increases. The more uranium-238 I remove, the more pure uranium-235 I am going to get. And by the way, I only need to achieve a purity of 3, 4, 5% for a nuclear reactor. So 0.7% is not good, but 3%, 4%, 5%, that's quite good for nuclear reactor. However, if I want a nuclear weapon, an atomic bomb, then this same enrichment will go in the enrichment percentage of 90%. That we will need 80 to 90%. We will need almost pure uranium-235. Uranium-235 with enrichment of 90 or even more than 90%. जितना ज़्यादा enriched होगा, उतना powerful आपका nuclear weapon होगा. But for nuclear reactor, 3, 4, 5% of enrichment is more than enough. So we will have to use isotopic separation methods, which by the way are much more difficult to achieve compared to when I describe it to enrich uranium. So आप लिख सकते हो in the enrichment process. So give this heading enrichment. Next is enrichment. Natural uranium comprises of more than 99% of uranium-238, which is not a good fissile material, It has only, or it has even less than 1% of uranium-235. Less than 1% of uranium-235. The purpose of enrichment process is to increase the concentration of uranium-235. The purpose of enrichment process is to increase the concentration of uranium-235. Up to 3 to 5%. Using isotopic separation methods. Isotopic separation methods. अब इसमें एक लाइन लिख सकते हो, for an atomic bomb, the enrichment percentage should be in the range of 90%. Enrichment percentage should be in the range of 90%. Enrichment percentage should be in the range of 90%. Range of 90%. So enrichment is one of the most important part of this fuel cycle. But we then finally have to give the final form to the fuel. हर fuel का अपना खुद का form होगा. So what does fabrication include is that जो enriched uranium है, now we are going to convert that into spherical or cylindrical pellets of not very large size. So a spherical pellet, a uranium pellet will look something like this. It can be a cylindrical pellet. And we have to make many of these small pellets. Like literally their size will be this much huge, this much big. And all of these pellets will be embedded into a rod, a metallic tube. Inside a metallic tube, all of these pellets will be kept. And ये जो metallic tube है, it has all these uranium pellets. I will call it fuel rod. Along with fuel rod, we will keep control rod in the core of reactor. But at one point of time, there will be about 150 to 200 fuel rods working together. So 200 fuel rods together, I can call it an assembly of fuel rods. And when nuclear reactor operates, then at one point of time, we keep at least 100 to 150 assemblies simultaneously, so that we can keep replacing it whenever it is required. And so at one point of time, once the core of the reactor has been filled with enough fuel, control rod, all of the arrangement, and once it starts become operational, that fission starts happening, it is not going to stop for about a year or even 2 or 3 years. So nuclear reactor can produce continuously energy for 2 to 3 years also. And larger nuclear reactors can have capacity of 700, 800 megawatt of capacity. But we do not have to refuel it for Minimum 1 year, but it can be of even up to 3 years, depending upon what type of nuclear reactor we are talking about. That is what nuclear fission at the reactor includes. तो आप लिख सकते हो fabrication includes making enriched uranium pellets, embedded into a metallic tube, which is called fuel rod, Many fuel rods are kept together as an assembly. It may look something like this, that you have all of these fuel rods, more than 100, even up to close to 200 also, all of them kept as an assembly, and I will have many such assemblies, more than 100 such assemblies in the core of the reactor. Write down next, give the next heading, nuclear fission at the reactor. इसमें बस एक लाइन लिख लेना, it can continue for 2 to 3 years. It can continue for 2 to 3 years. Story has not ended here. When we burn diesel and petrol, that burning produces a lot of gases, atmospheric gases, particulate matters, which contributes to air pollution or global warming, environmental issues. When we burn coal, same thing, produces carbon dioxide, but many other pollutants also, contributes to air pollution. The leftover product is byproduct, which is a fly ash. Fly ash, if not handled properly, can contribute water pollution, soil pollution, air pollution, all sort of things. So waste in general is a challenge. Waste management in general is a challenge. But no, this challenge is the biggest challenge when it comes to nuclear waste. So nuclear waste is not simple waste. It is one of the most dangerous waste out there. It is highly radioactive. I will explain radioactivity in today's class itself, if time permits. So it is highly radioactive. It emits dangerous radiation of alpha, beta, or gamma particles. I will explain what those alpha, beta, and gamma are. And exposure to particularly gamma radiation can be fatal. If you are exposed to high doses of gamma radiation, it can immediately kill you, or even very small dose can increase the chance of having diseases like cancer. So nuclear waste is a dangerous waste, and this has to be handled with utmost care, with lot of safety considerations. What do we do then? Once nuclear fission stops, the assembly has exhausted, that assembly will be removed, and that assembly will be kept into a deep pool of water. Within this reactor building, there will be a pool of water at least 20 to 25 feet of depth. And we will keep all of that nuclear waste in the depth of this water, 25 feet depth of water. Now, water, turns out, is an amazing thing. Water can absorb that dangerous radiation, and it will not allow that radiation to escape into the atmosphere. But we do not do that for a day or week or a month. We do that for 3 to 4 years. So once that nuclear waste is removed, another challenge of nuclear waste is that the radioactivity does not die down. Radioactivity theoretically can exist for unlimited time. Practically depends upon a lot of parameters, which we will discuss in next class. So that radioactive waste which we have removed from the core of reactor has to be kept for 3 to 4 years into a deep pool of water, so that most of the radioactivity dies down and water absorbs the dangerous radiation. Once that happens, even then this is not safe. Even then it is radioactive. We can do two things here. What few countries do here is, such as US, they directly jump from here to here. You can make a arrow in your diagram जो हमने लिखा था, वे arrow बना सकते हो. That some countries, they can directly now find locations where this nuclear waste can be deposited. Often those locations will be deep geological formations. कि कहीं पे या तो artificially हम reservoir बनाए. पहले जो nuclear waste होगा, we will have to kept into a solid cascade made of very thick concrete, so that even if some radiation is being emitted, it will be absorbed by the concrete part itself. And then this thick cascade of concrete has to be kept in deep geological reservoir where it cannot escape for hundreds of years. In hundreds of years, radioactivity will die down. No longer it is dangerous, but we have to manage that nuclear waste with lot of safety. Some countries, such as India, what we do, we try to recover useful things. That the same way we talk about recycle, reuse in environment, in case of nuclear waste also, maybe there is something useful here. So nuclear waste हमने इस पानी से निकाला है after 3 to 4 years, maybe there is something useful here. Maybe there is fuel for the next set of reaction. How will that happen? I'm going to explain in the very next topic. That maybe there is fuel for the next reaction, and now we can use that fuel in the next set of nuclear fission reaction, and that is what this arrow is. So such fuel cycle is called closed fuel cycle, because if you look at only this part of the cycle, it's like a closed loop cycle. So such fuel cycle where we are trying to use spent fuel reprocessing, where we are trying to recover fuel from the nuclear waste, is called closed cycle. Our nuclear energy program very much depends upon closed cycle. But many countries, they go for open cycle. They do not go for spent fuel reprocessing. US is the best example. US does not go for spent fuel reprocessing. They directly jump from here, and then they find suitable locations where that nuclear waste can be deposited. This is what nuclear fuel cycle is all about. तो आप लिख सकते हो, give this heading, interim storage. Interim storage. Interim storage. In the very first class, I asked many of you, and that is applicable to online students also, that wait for the topic to be completed. I will give you ample of time to ask questions. Lot of the questions you are asking, we'll be discussing about it. So I'll give you ample of time, don't worry. Anyways, in interim storage, write down a line here. Once fission stops, the byproduct, dangerous radioactive nuclear waste, is removed from the core, and kept in a deep pool of water, for few years, easily for 2 to 3 years, for few years. Next, spent fuel reprocessing. This includes recovery of useful substances. Such as fissile material from nuclear waste. This includes recovery of useful substances such as fissile material from nuclear waste. And final disposal. The remaining waste has to be disposed of The remaining waste has to be disposed of in deep geological formations, burying in solid casket, burying it in solid casket, burying it in solid casket. Burying it in solid casket. यहाँ पे two most important things in this entire fuel cycle. I want you to know about or appreciate the two most important part of the fuel cycle. The first is enrichment part, and the second is spent fuel reprocessing part. That enrichment is one of the most essential part of fuel cycle, and particularly for India, that spent fuel reprocessing is another very important part, that we try to recover useful things from nuclear waste. Now let me come to the main, one of the most important topics we should know about here is, give this heading, Nuclear Energy Program of India. Nuclear Energy Program of India. So what has India done till now? Or what are the major plans, what India has achieved in nuclear energy production till now? And we have to go back into history here, and we have to look at the geopolitical conditions, and we have to look at how India has to develop its nuclear power policy given the geopolitics around it. So let's directly go back to our independence, that in 1947 we became independent. Just 2 years ago, World War II had ended. And World War II, even though US and USSR, they fought together against common enemies, Germany, Italy, and Japan. But it was very clear, so before war they were enemies. During war it was very also clear, in 1945 it was clear that once the war ends, they are again going to emerge as enemy. I'm talking about US and USSR. Because there was a common threat, they had united. And this is exactly what happened. In fact, a lot of experts talk about that the atomic bombs US used on Hiroshima and Nagasaki, that was for Japan so that they can escalate the surrender part, of course, but the purpose was all to showcase their capability to USSR, that don't think after the war you are equal to us. But USSR very soon, they had their own spy program, they had known the key secrets of the nuclear power program, nuclear bomb program of US, and very soon they developed their own nuclear bomb in 1950s itself, just few years after end of World War II. That entire period from 1945 to 1991 is called period of Cold War. Why we call it Cold War? Because US and USSR, they did not fight a direct war together anywhere, but they did participate into many indirect wars, and they came very close to war. Just they fought in Korea, they fought in Vietnam, they came almost close to fighting an actual war in Cuba, Cuban Missile Crisis. So all of that happened, and this entire period is also known for race among these two countries, US and USSR, in many areas. One of that was nuclear race, that there was now a competition going on, that who gets to develop how many number of nuclear bombs. And both US and USSR, they conducted many nuclear tests in deserts, inside oceans, even in atmosphere, right? That is one part of it. But what has that to do with India? Because for a developing nation like India, who has just become independent, one of the great pressure is that you have to side with somebody. You have to side with US or you have to side with USSR. Pandit Nehru decided that we have faced the issue of colonialism for a lot. We are going to follow our own independent foreign policy, and we are going to something called non-aligned movement. It will be taught in detail in higher classes, that we are not going to align ourselves with US or USSR. But this particular thing had a direct impact on our nuclear policy. There was a fear that more and more countries will develop nuclear weapon, right? So there was a fear, and because of that fear, uranium became a very restrictive commodity, that you cannot supply uranium to a country whose allegiance is not very clear. And India's allegiance was not at all clear at this point of time that, and India said that we do not want to ally with anybody. We want to pursue a non-alignment policy. However, we were closer to Russia, closer to USSR. That part, I think everybody is very clear about it. And particularly when Indira Gandhi became Prime Minister, it was very clear that we are much close to USSR than America. One of the greatest nuclear scientists world has ever witnessed was Dr. Homi Jahangir Bhabha, and he was an Indian scientist. So Dr. Homi Jahangir Bhabha realized the geopolitical complications and realized that nobody is going to give you uranium directly. And India does not have a lot of uranium. This is also unfortunate that uranium बहुत सारा है, but India में बहुत सारा नहीं है. We do not have a lot of uranium. We have some uranium. Dr. Bhabha was responsible. He was in fact the project head when we developed the first nuclear reactor in 1950s itself called Apsara. You may have read about it. The very first nuclear reactor we developed was called Apsara. But Dr. Bhabha is known for envisaging this grand plan spanning few hundred years, not few years, few decades, few hundred years, which we call three-staged nuclear energy program. And this is my main topic when I am talking about nuclear energy program of India. So give this heading, three-staged nuclear program of India. Subheading within this discussion, within this main topic. तो पहले तो बैकग्राउंड ये 3 stages में क्यों हमको डेवलप करना है. So name should clarify here that we aim to develop our nuclear energy program into 3 distinct stages. 3 distinct but also related with each other. Why those 3 stages? Geopolitics will answer the question. That India does not have a lot of uranium. Nobody is going to give you uranium directly. We have some uranium. What we do have is thorium. There is a very important mineral called thorium. Thorium has atomic number of 90, and the most abundant thorium in the world is thorium-232. Thorium has also many isotopes. The most famous isotope is thorium-232. Thorium is found a lot in Western Ghats. Entire Western Ghat, but also in Eastern Coast, but mostly in Western Ghat, particularly in Kerala. In Kerala, you have a type of sand called monazite sand, and monazite sand has huge amount of thorium. So Dr. Bhabha was very clear that we do not have a lot of uranium, we have some, but we do have a lot of thorium. The problem is that uranium-238 is not a good fissile material, and so is thorium-232. So thorium-232 is also not a good fissile material. But they can be converted into good fissile material. We can have a nuclear reaction where they can be converted into something else, and that something else will become a good fissile material. But for nuclear reactions, we need a lot of energy, and that energy we can use, that energy can be used from the nuclear reactor itself. So why 3-stage program? What it actually included? Again, you can make this flow chart. I'll explain this in detail, but first make the flow chart. So first stage include a pressurized heavy water reactor. I already have told you that in pressurized heavy water reactor, we use heavy water as moderator and coolant. In pressurized heavy water reactor, we will be using uranium, whatever uranium we have. So uranium is uranium-235 plus uranium-238. Uranium-235 that will undergo fission, and that will produce energy. But uranium-238 will not go into vein. Some of that uranium-238 at such high energy process can absorb a neutron. And by the way, this reaction happens in 2-3 stages. The end result of this reaction will be that it will produce plutonium-239. It should be very clear that this is not a direct reaction. You have 92 uranium-238 absorbing a neutron, producing 94 plutonium-239. Now clearly neutron absorption will increase the atomic mass, 238 plus 1 neutron, 239, but that does not explain that 92 to 94. Hence, I meant that this reaction happens into 2-3 stages. I am only writing the end result. That uranium-238 can be converted into plutonium-239. So while uranium-235 is called fissile uranium, lot of times you'll come across this term fertile uranium. So uranium-238 is called fertile uranium. Fertile in the sense that even though this is not a fissile material, it can produce a fissile material. Fertile uranium and fissile uranium. This was first stage. Then in first stage, we will have pressurized heavy water reactor. Whatever uranium we do have, we are going to use that uranium. We will produce energy from nuclear energy. But that uranium-238 will not go into vain. It will convert into plutonium-239. At this stage should go for 30 to 40 years. In 30 to 40 years, using spent fuel reprocessing, we will collect enough of plutonium so that we can enter into the second stage. The second stage will be a fast breeder reactor. So now I'm going to explain this fast breeder reactor. In fast breeder reactor, few things will happen. The plutonium-239 which you have recovered from the first stage, remember I told you about spent fuel reprocessing, that we will try to recover some useful fissile material. That we will do from nuclear waste. We will try to recover plutonium-239. Once you have enough plutonium-239, turns out this is a very good fissile material. Now plutonium is not abundant in nature. Uranium is abundant, but plutonium actually is quite a rare mineral. So whenever we make plutonium out of uranium. That uranium undergoes some sort of nuclear reaction and it can be used to make plutonium or some other heavier nucleus. So plutonium is not a abundant mineral per se, but we can make plutonium inside that nuclear reactor itself at very high energy. When uranium absorbs neutrons, it finally converts into plutonium. So we will be using this plutonium. We can add uranium-238. We still have uranium. We can add uranium-238. So plutonium-239 can undergo fission, can produce energy. Uranium-238 can absorb a neutron and produce plutonium-239, which will be used in the second stage itself, but that is not the most interesting part. The most interesting part here is that we will also be adding thorium here. And thorium can absorb a neutron, and this can convert into uranium-233. And thorium की हमारे पास कोई कमी नहीं है. We have lots and lots of thorium. Enough of thorium. In fact, 1/4 of thorium reserve in the entire world is found in India. So thorium reserve की हमारे पास कोई कमी नहीं है. But thorium is not directly useful. We need to convert that thorium into some fissile material, and a good fissile material can be uranium-233. So let me tell you a few more things about fast breeder reactor. In fast breeder reactor, we use liquid sodium as coolant, and we do not use any moderator. तो एक जो सबसे important feature है fast breeder reactor का, that we use liquid sodium as coolant, and we do not use any moderator. I just told you a few minutes ago that we use moderators to slow down the speed of neutrons, and I also told you that slower neutrons are better at causing fission. So clearly faster neutrons are not very good at nuclear fission. Then why this reactor? Turns out that slower neutrons are not good at fission, but faster neutrons are not good at fission, but faster neutrons are really good at that reaction, that thorium conversion into uranium-233. And the reason we call this reactor fast breeder, breeder का क्या मतलब होता है? Some sort of reproduction. It is breeding, but it is breeding faster than consumption of plutonium. So the rate of production of uranium in fast breeder reactor will be more than rate of consumption of plutonium-239. Hence the word fast breeder reactor. So why we are not using any moderator here? Because fast neutrons are not good at fission, but fast neutrons are really, really good at converting that thorium into uranium. And we will produce much more uranium than the consumption of plutonium-239. This stage will also go on for about 30 to 40 years. And once you have enough uranium-233, then we will enter into the third stage. Third stage, one of the type of reactor we are exploring. We are not closer to third stage at all, but a type of reactor we are exploring is called advanced heavy water reactor. In third stage, we will be using uranium-233, but we have lot of thorium. And uranium-233 can undergo fission, and it can produce energy, but that thorium can convert into uranium by absorbing a neutron, and we can keep converting that thorium into uranium, and we can keep producing energy. And we have so much of thorium, the third stage can go on for about 400 to 500 years. So while first and second stage for 30 to 40 years, third stage can now go on for 400 to 500 years, and we can produce a lot of energy. We have so much amount of thorium reserve available. So this was this plan envisaged by Dr. Homi Jahangir Bhabha to overcome the limitation of lack of uranium, but abundance of thorium. However, thorium is not a fissile material. So how can we convert thorium into a fissile material? And second stage is crucial for that. So second stage hai, that is a very crucial stage, where we start converting thorium into uranium. This is one of the most important topics for this year's examination and for next year's examination, because ये plan ideally second stage में we should have, जैसे मान लो, let's say that I start my first stage in 1960s. Then by 1990 or by 2000, I should have entered into the second stage. But we have finally entered into the second stage just last month. So why this topic is important? Because the very first fast breeder reactor has finally started, we have started loading fuel in the core of the reactor. That is located in Kalpakam, Tamil Nadu, and that is the very first fast breeder reactor. So India has officially entered into second stage just last month. And that is why I think this is one of the most important topic for this year's or next year's examination. But nuclear energy will remain an important topic in coming times, because Government of India has a lot of focus on nuclear energy here. So now write down few more things about the three stage. This was envisaged by Dr. Homi Jahangir Bhabha. This was envisaged by Dr. Homi Jahangir Bhabha. The three-stage program was envisaged by So the same way we think of Dr. Vikram Sarabhai as father of India's space program, Dr. Homi Jahangir Bhabha is father of India's nuclear program. In fact, Dr. Bhabha had a very mysterious death. He died in a plane accident, and many people believe that this was not an accident. This was a proper assassination which occurred on the behest of CIA. CIA was not very happy with the development of nuclear program, given the fact that India was, even though officially NAM, non-aligned country, but was closer to USSR. So many experts think, and no longer it is a conspiracy theory. In fact, many genuine people think that Dr. Bhabha, he died not in an accident, but that was an assassination. But nonetheless, Dr. Homi Jahangir, he was nominated thrice for Nobel Prize in Physics. Had he lived, perhaps he would have won also. Nobel Prize is not given posthumously, that is there. So Dr. Homi Jahangir Bhabha would have perhaps received a Nobel Prize also. So he is one of the greatest scientists in the field of nuclear science, not in India, but of the world. So write down few things here. It was envisaged by Dr. Homi Jahangir Bhabha. India has some uranium reserve. India has some uranium reserve, but huge amount of thorium, huge amount of thorium found in Western Ghats, particularly in monazite sands of Kerala, particularly in monazite sands of Kerala. The three stages includes write down in bullet points. In the first stage, PHWR, pressurized heavy water reactor, PHWR, will be utilized for energy production, using uranium-235, U-235, but uranium-238 can undergo a transmutation. Transmutation means converting into something else. Transmutation by absorbing a neutron, it can convert into plutonium-239. Write down next bullet point, next paragraph. In the second stage, fast breeder reactors will be used. Fast breeder reactors will be used. With no moderators, and liquid sodium as coolant. With no moderators and liquid sodium as coolant. Plutonium recovered from the first stage will be used for fission, along with a blanket of thorium, which can convert into uranium-233. इसमें एक लाइन ऐड कर सकते हो. Fast neutrons are not good at fission. But they can readily convert thorium into uranium. In fact, it is called fast breeder. In fact, it is called fast breeder. In fact, it is called fast breeder because it produces more uranium. It produces more uranium than fission of plutonium. Than fission of plutonium. And the most important line, write down. Recently at Kalpakam, Tamil Nadu, recently at Kalpakam, Tamil Nadu, fuel loading had started in a fast breeder reactor. Fuel loading had started in a fast breeder reactor. ये आपका पहला बैच है जिसमें मैं लिखा रहा हूँ. इससे पहले I was always critical that अभी तक नहीं हुआ. So finally we have started the fast breeder reactor. Give the next heading, third stage, or the next paragraph. In third stage, uranium recovered from second stage. Uranium recovered from second stage will be used. Uranium recovered from second stage will be used along with thorium. Because of abundant thorium reserve. Third stage can produce energy for few hundred years. Third stage can produce energy for few hundred years. Third stage can produce energy for few hundred years. I have taken this picture from Bhabha Atomic Research Center, one of the research organizations under Department of Atomic Energy. And they have talked about all of this theoretical data input, that for 30 years, 12 gigawatt electricity, 300 gigawatt for 30 years, but 500 gigawatt of electricity for 500 years in the third stage. That is the theoretical calculation if everything happens with proper efficiency. Clearly it has not happened, despite the fact that we have entered into second stage. What should have occurred at least 10 or 20 years ago. So what has ailed India's nuclear energy program? Like, just to give you some context, हमारा जो total installed capacity है, we produce our total installed capacity in energy as of now is 430 gigawatt. 1 giga is 1000 megawatt. So 430,000 megawatt if I have to approximate. Out of that 430 gigawatt, the contribution of nuclear energy is less than 2%. It is in fact about 1.7 or 1.8%. That is a very less contribution. Many countries, US for example has contribution of 15 to 16%. Even Pakistan has contribution of 5 to 6%. So many countries have this contribution of nuclear energy in double digit. So what has ailed India's nuclear energy program? And why has this three-stage program not worked as it was envisaged? Let's take a break here. After that, we will discuss this. There is a question कि याद रखना पड़ेगा या concept समझना काफ़ी है. But अगर आप concept समझ गए तो आपको याद नहीं हो गया फिर. Like why these are not two mutually exclusive things. If you understood the concept, then you automatically have, of course, remembered it. There is a question that there is no other technology development since then. ऐसा बिल्कुल भी नहीं है. Dr. Bhabha thought of a more or less plan, but a lot of changes we have made after that. He is saying this, that no other technological development has occurred since the envisaging of this plan is not at all correct. A lot of changes were occurred. Depending upon the limitations, a lot of changes were introduced here and there by Department of Atomic Energy. This three-stage program has not worked really well. To appreciate that, we need to critically evaluate nuclear energy itself. That let's do a critical evaluation of nuclear energy. There are certain issues with nuclear energy. I already have told you one of the issues is how to manage radio waste, the radioactive waste that is very dangerous, and managing it in itself is a huge challenge. But there are other problems also. There has been fears of nuclear reactor meltdown, some accident in the core of the reactor. Let's say if the reactor becomes uncontrolled, if you cannot control the reaction, it will lead to an explosion, it will lead to meltdown. And this is not theoretical, by the way. It already has occurred. So for example, in 1986 in Chernobyl, which till now, erstwhile it was part of USSR, but right now it is in Ukraine. So in Ukraine you had this reactor, in Chernobyl you had this reactor. And this reactor had some flawed design, and the people who were working there, they were even like, they had their own propaganda in their mind. And there were many problems with Chernobyl reactor which had been highlighted by many scientists. But those warnings were simply ignored because in authoritarian regimes, remember the biggest problem of authoritarian regimes is that as long as things are going well, it's fine. The moment start things becoming bad, then nobody will be willing to take up the responsibility. So first people will not even accept responsibility. First people will not even accept that a mistake has occurred, that something wrong has occurred. And that is why political dialogue is very important. That you enter into a dialogue, you understand the differences, and despite those differences, then you find onto some sort of consensus. So USSR, communist regime, authoritarian regime, many people had highlighted that there are problems at Chernobyl, but those warnings were ignored. Finally, there was an explosion. It was not a simple reactor meltdown. The core literally burst out. Like there was an explosion and the core completely burst out, and everywhere the nuclear waste now got spread. When this was informed, then the group of people who were responsible for managing this reactor, they said that it has not happened. Like they literally said that it has not happened. They were not willing to accept it, that something like this has happened. And even worse, that the local communist leadership, they decided that if this news becomes big, then there will be a lot of central leadership, they will remove a lot of people, will be thrown to jail perhaps. So what they did, they locked down the city. That if a lot of people start fleeing out of the city, then this will cause a panic, and this will go, the entire local leadership will go into a bad name into central leadership. So they locked down the city that nobody will be allowed to leave. So immediately that night itself, when the reactor meltdown happened, many people died, but in next few 6-7 days, few thousand people died a horrible death. And nuclear reactor radiation ka jo death hoga, that will be a horrible death, by the way. So it is not theoretical. It already has happened. So Chernobyl disaster is, Chernobyl disaster, however, was a man-made disaster. A lot of warnings were given, those warnings were ignored because the regime and the leadership, they did not want to accept their mistakes, that they have caused some mistakes. I will not go into details of what those mistakes were. That's not important here. But then so in India, there has always been a very powerful pressure group which has opposed nuclear energy production, nuclear power plants. There have been many NGOs who oppose nuclear power plants. And Chernobyl disaster fueled that. But then one more disaster happened in Japan. Now Japan is a responsible country. A regime, authoritarian regime, not a responsible nation, but Japan is one of the most responsible country. So in Japan, there was a reactor at Fukushima. Fukushima is a place, a coastal city. And at Fukushima, you had reactors. But Japan, it's situated, geography may you will be taught about Pacific Ring of Fire. Japan is situated at a place where a lot of plates are very active. And Japan witnesses a lot of earthquakes. And if those earthquakes become severe enough, they can trigger a tsunami. And this is exactly what happened in 2011, that everything was done perfectly well, no human error, but then a tsunami occurred. What do you do when a tsunami occurs? So the nuclear reactor was destroyed at Fukushima. And by the way, that led to a severe reaction against nuclear energy, and many countries decided that we are going to roll up our nuclear energy production. We will not produce energy using nuclear energy. And just 3 years ago, in 2008, a remarkable deal had occurred between India and US. This is called nuclear deal between India and US. But in fact, let me tell you a few more things in past, that what has been some of the most iconic moments in the history of nuclear science and technology in India. I talked about Apsara reactor, I talked about 3-stage program. When Indira Gandhi was Prime Minister, we did the first Pokhran test, the first nuclear atomic bomb. And the very first test that infuriated a lot of people, we did not continue that. At that point of time, we did develop enriched uranium, but we did not continue that. It was abandoned because of the diplomatic pressure. However, countries made up a group called Nuclear Supplier Group. Nuclear Supplier Group is a group of nations that they can supply uranium to each other, but you cannot supply uranium to somebody who is not part of the Nuclear Supplier Group. Now, to become a member of Nuclear Supplier Group, you need 100% vote. It's not majority vote. Even one member can veto addition of new member. And one member always vetoes India's membership, that is China. So even today, India is not a member of Nuclear Supplier Group. And that, by the way, that group was created after that Pokhran test in 1968, 1969. After that, we did not invest a lot into nuclear bombs, but we did invest into nuclear reactor, although things were not going as we had hoped for. In Chernobyl disaster, when it happened in 1986, there was a severe reaction against nuclear power that stalled our nuclear energy program. And we had a lot of support from Russia, which was at that point of time was USSR. So we had a lot of support from USSR. But when Cold War ended, and Cold War finally America was victorious in Cold War, that when USSR got disintegrated, then they had their own set of issues. They are not there to help India per se in our defense or nuclear requirements. So we were on our own. That also did not help. But then when Vajpayee became Prime Minister, then despite a lot of diplomatic pressure, India now successfully conducted again Pokhran 2. And now India announced to the rest of the world that we have atomic weapon. We have developed an atomic bomb here. That led to a furious reaction from all parts of the world. A lot of sanctions were imposed upon India. And because there was a fear that India will emerge as an irresponsible nuclear nation. We have Pakistan at our neighborhood. Maybe India will use its nuclear weapon. So the next few years was quite difficult diplomatically, that India had to show that we are a responsible nuclear power nation, and we did a lot of things. For example, we announced to the world that we have a no first strike policy, which essentially means that we will never attack a country with nuclear weapon, but we have the right to retaliate. We are going to retaliate if somebody else has attacked with nuclear weapon. India also said there is an agency at the global level which operates under United Nations. The name of that agency is International Atomic Energy Agency, IAEA. India said that I invite IAEA observers to come to India. And if you have a fear that if you supply uranium to India, then maybe India will start enriching it for nuclear weapon, then you come and look at our enrichment facilities, and you yourself can see that if we are enriching uranium for weapon or for reactor, for imported uranium, whatever uranium we have extracted from our own mines, of course we have our own, that is within our sovereign jurisdiction. We will not allow inspection there, but India adopted a 100% transparency policy in case of imported uranium. And that led to a remarkable deal between India and US in 2008, that despite the fact that India is not a member of Nuclear Supplier Group, India got a special waiver from Nuclear Supplier Group that countries can enter into its own bilateral arrangement with India. And US became the very first country. This did not materialize, but it paved way for agreements with other countries. And as of now, India has agreement with multiple countries regarding uranium supply. So India has agreement with Canada, with Australia, with Japan also. And why I'm emphasizing upon Japan? Because Japan does not enter into a nuclear deal unless you have signed a treaty called Non-Proliferation Treaty and CTBT. Basically, you do not have to stop your nuclear atomic bomb program. Japan is quite serious about it because Japan is the only victim of nuclear attack. But in case of India, Japan made an exception that despite the fact that India is not a signatory of these treaties, global treaties, we have a nuclear deal with Japan. So it seemed like that in 2008, when Dr. Manmohan Singh was Prime Minister, that things are finally going to fall into place, and India will emerge again. The entire nuclear power program is going to escalate, will find some momentum. But then Fukushima happened in 2011. And that pressure group, which always has been there, it became again very active. And there was a lot of opposition to nuclear energy program in India. So that further derailed our nuclear energy program. And in the same decade, last decade basically, lot of focus was given on solar and wind energy. Now solar and wind energy, they were very expensive, but because of research and developments in US, in Germany, manufacturing in China, the cost of solar energy production came down a lot. And solar is renewable, no fear of any nuclear waste per se. So many countries, including India, focused a lot upon renewable energy sources rather than on nuclear energy sources. So all of that, compounding of all of those factors, has led to a situation where even today the total capacity, installed capacity of nuclear power is less than 2% in India. So this will be why three-stage program has not worked really well. आप लिख सकते हो? Give this heading. Challenges in implementing three-stage program. Implementing three-stage program. Three-stage program. Write down few things. Spent fuel reprocessing. Spent fuel reprocessing. Spent fuel reprocessing is risky, complex and expensive. Risky, complex and expensive. What does that mean here? That I told you that we aim to convert uranium-238 into plutonium-239. So saying that and on writing on piece of paper is of course very simple, but actually doing it and then recovering it is much, much more difficult and expensive. So that is what I mean by this first point. Write down in second point. There are many fears associated with nuclear energy. There are many fears associated with nuclear energy. Distributed. There are many fears associated with nuclear energy. There are many fears associated with nuclear energy, such as nuclear waste management, nuclear waste management, reactor meltdown, fear of natural disaster, fear of natural disaster such as powerful earthquakes or tsunamis, fear of natural disasters such as powerful earthquakes or tsunamis, You can write down few examples also. For example, Chernobyl disaster, (1986). At that point of time, it was part of USSR, but as USSR disintegrated, it has become Ukraine. There is a reason why Ukrainians do not like Russian regime. They have their own culture, they have their own language, and this imposition of Russian language and culture on Ukraine and such type of events, that has not done any good in the psychic of Ukrainian people. So Chernobyl disaster, 1986. Fukushima disaster, Fukushima disaster, 2011. This happened in Japan. Third point you can mention. India is not a member of nuclear supplier group. India is not a member of nuclear supplier group. India is not a member of nuclear supplier group. आप एक लाइन इसमें लिख सकते हो, although we have a waiver from NSG, India has a waiver from NSG. India has a waiver from NSG. And as of now, India has entered in bilateral nuclear deals with many countries. Bilateral nuclear deal with many countries. Bilateral nuclear deal with many countries. And one last point you can add. The cost of renewable energy has come down significantly in last decade. The cost of renewable energy has come down significantly in last decade. I'm talking about solar and wind. The cost of renewable energy has come down significantly in last decade. There has been more focus on these resources. There has been more focus on renewable energy resources. There has been more focus on renewable energy resources. All of that together leads to a situation where three-stage program has not functioned that well, like the way we had hoped for. There was a very good question asked by UPSC. Write down a question here. Should India keep on expanding? Should India keep on expanding its nuclear energy program? Should India keep on expanding its nuclear energy program? Discuss the facts and fears associated with nuclear energy in this context. Discuss the facts and fears associated with nuclear energy. Discuss the facts and fears associated with nuclear energy in this context. I'll repeat the question. Should India keep on expanding its nuclear energy program? Discuss the facts and fears associated with nuclear energy in this context. I will give you 9 minutes here. Think of a detailed approach that what are you going to write in this particular question. Whenever you feel ready, it does not have to be 9 minutes. Whenever you feel ready, you can share your approach with the rest of the class. Ideally, I would want not familiar faces. I want more and more people to participate, that what can be written in this particular question. Online students also, you can post your response on the response portal. In fact, 5 minutes only, not 9 minutes. I will only give you 5 minutes. There were few words before this question. Given the growing energy need, should India keep on expanding nuclear energy program? So there are like few words which I had forgotten. Given the growing energy need, should India keep on expanding its nuclear energy program? That was the exact question asked by UPSC. That does not change the answer a lot, just to give you some context. Given the growing energy need, should India keep on expanding its nuclear energy program? I already have received few responses by online students. So anyone else in the class anyone in the class would want to add, want to contribute your answer, share your answer? Yes, go ahead. First talk about your approach, like what is the approach you adopted? What's your name? Okay, Priyanshu. First share your approach. No, no, I just want an approach, not the bullet points. Okay, ठीक है. Fissile material, yeah. What is your conclusion? Safety part. That's a very good answer, by the way. That's a very good answer. Yes, go ahead. You have to be louder. I'm really sorry. You have to be louder. Don't write your, I do not want the complete answer. I just want the main bullet points. You've done all that in 6 minutes. That's marvelous. So, but all of these are very valid points and very good points. One part which you should talk about is, because it is a question about opinion, and we do not form our opinion without looking at both sides of the argument. So look at the challenges part also. So that part is missing in your answer, but otherwise, all of these are very valid points. I don't think these two parts are separate parts. Fundamentally, the question is that should India or should India not? This is an opinion-based question. In opinion-based question, you have to write proper conclusion. Your conclusion does not have to be like 2-3 word lines, a proper, well argued conclusion. But before I can conclude, do not start your answer with yes or no. Do not do that. Always and always look at the both sides of the argument, both sides of the coin. You do a cost-benefit analysis, and then finally you weigh down your own argument that what should be the way forward, given the cost and given the benefits. So in general, in all opinion-based questions, this is a fundamental approach you have to adopt, that you do not directly jump to the conclusions. You look at all sides of the arguments, and then you do a proper critical evaluation, and finally you conclude. There can be few types of introduction here. You can define nuclear energy. Simple, that can be introduction. Or many online students, for example, have talked about that how we can mention about growing energy need. If I have some data point, if I know how much energy capacity we have, how much energy capacity we are expecting in next, let's say 5, 6 or 10 years, and there are really good data points available on Niti Aayog's website, on Ministry of Power website, that what is our target for 2030 or 2050. Even if you do not have any data point, you still can mention few things like the fact that we have a growing population, we have growing economy, and both growing population, growing economy essentially means that we need to produce more and more energy. So that can be a very simple starting point in the introduction itself. In main body, you are going to write the cost of nuclear energy as well as the benefit. So we'll be talking about facts, दोनों side में आएंगे, fear खाली आपका challenges में आएगा. So we'll first talk about benefits. Now what are the benefits? We can mention, as rightly pointed out by many people, that it is a clean source of energy. By the way, when we use the word clean source of energy, we only and only talk about that what is the carbon footprint here. So clean source of energy should not, for a second, you should think that it does not produce any waste. In fact, it does produce waste, and it is a dangerous radioactive waste. That should be very clear. When I'm saying clean source of energy, then it means that it is not producing CO2, CH4, N2O, all of the greenhouse gases responsible for global warming. You are going to start with that. It is a clean source of energy. Second, you will mention about, jaise, I'm very sure few of you, or perhaps all of you, know about India's environmental obligations, that we have announced at the global stage that by 2070 we are going to become carbon neutral. We can associate that target with nuclear energy. That because nuclear energy has very less greenhouse gas emission, India can fulfill its environmental obligations of reducing carbon footprint. We can mention that. We can talk about the fact that nuclear energy has very high energy density. With very small amount of fuel, we can produce huge amount of energy. You can talk about the potential of thorium. You can talk about the efficacy of 3-staged program. We haven't even mentioned nuclear fusion abhi, but nuclear fusion perhaps can also be mentioned in the first part of the answer itself. Go to the second part, challenges. What will be the challenges? You'll talk about fear. You'll talk about fear of reactor meltdown. You'll talk about fear of nuclear waste management. You'll talk about opposition from local people. You'll talk about the cost, initial cost of nuclear reactor establishment is very high. And keep giving examples. Just give the example of Chernobyl, or give the example of Fukushima disaster. Talk about renewable energy cost that has come down. So talk about all of those things. Then you have to conclude. And conclusion का एक जो बहुत central theme जो आपका होना चाहिए, that should be energy security of India. That energy security is one of the most important national goals for any country. And nuclear energy can be a very important tool. Energy security includes two things. First, that you are able to produce enough energy and you are not dependent upon from other nations. Self-dependency is very important. And second, that ideally that energy should come from various sources. That is called diversification. जो आपका energy basket है, that should be diversified enough. That just in case you are dependent, and by the way, India is very much dependent, then even if one of these sources is affected, which is not in your control, for example, think about how Russia-Ukraine war started or Israel-Palestine war, and how that leads to shooting of oil price. And that oil price now causes inflation into India. So ideally, we should try to be in a situation, of course it is very difficult to achieve, that the shock of external events should have minimal impact on India's economy. And energy security is a very essential parameter for that. And energy security does include energy diversification And yes, nuclear will be a very important part of that diversification. I don't think no is an answer. That no, India should not, I don't think that is an answer. India should, but with lot of focus on safety, with caution, and nuclear should not be the only thing. We should diversify further. We should expand capacity of solar, of wind, of hydro, of green hydrogen, and we should of course also expand the capacity of nuclear. But the focus should be on the safety part. The focus should be ensuring that waste management happens properly, right? So ये सारी चीजें हम लिखेंगे. That answer is yes, but with caution. That we have to also talk about the caution part. So this is a question where you have to write an elaborate conclusion based on a proper cost-benefit analysis. That can be your homework. Try to write this answer at home. I'm going to complete discussion of nuclear technology, but the class has not ended. You have all of you have a test paper in front of you. And online students also, please go to your portal. On your portal, you'll find in the handout section, you'll find a space technology quiz. The previous topic we have completed. You have 25 questions. So you get 2 hours for 100 questions. So I'm going to give you half an hour for 25 questions. My hope here is that you try to attempt all of that, but don't do it because there will be few questions which will be very difficult, you are not very sure about. But my hope here is that all of you attempt at least 15, 16 questions and maintain a high level of accuracy, even if you cannot attempt all of the questions. I will give you half an hour to complete this paper. Do not have to submit it to anybody. I'm going to discuss the answer once the test paper ends, and you can check by yourself that how much you have scored. So this is totally like you are accountable to yourself rather than you are trying to see that somebody is going to check your paper. So for half an hour, appear this test paper, just mark your answer on the paper itself, and I'm going to give you, I'm going to discuss all of these questions once the test paper ends, and you can check that how well you have done. Same goes for online students. Please download the paper and attempt the paper at your home. I will see you at 12:15. Class has not ended. I will see you at 12:15. How did you do? The paper? Difficult? Simple? I'm going to quickly tell you the answers. Briefly, I will discuss these questions. If you want detailed discussion, ask questions in the next class. Question number 1. First statement is not at all correct. Escape velocity for a heavier object is more than a lighter object on Earth. That is not at all correct. Escape velocity will be same irrespective of your mass. Such type of questions, if either of these statements is wrong, your answer is fixed. In this case, statement 1 is incorrect. Statement 2 is correct though. And heavier object will experience more gravitational pull. That is there. But the force also determines your acceleration. So I told you in the last class itself, or in previous classes I have discussed this. That a heavier object will experience capital G m by r square. So if you're small, if your mass is higher, then the force of attraction which you will feel, that will be greater. But escape velocity will be independent of your mass per se. Any object, if we give them, if we give 11.2 km per second, it's not going to return to Earth. यहाँ पे statement 1 is incorrect, statement 2 is correct, D is the correct answer. Question 2, what will be the answer? Question to answer will be A, that the inertia of car will carry it forward. Momentum is only conserved when there is no external force. Only then momentum of a system is conserved. Here, when you apply brake, friction will be an external force. So B in any case is not correct. The kinetic energy of the car must be conserved. Not at all. Why would kinetic energy be conserved? Total energy of car must be the total energy of this entire system will be always conserved, but car ka energy will not be conserved because of friction hai, that is a dissipative force. Friction ke karan a lot of heat will be generated on the ground and that energy will be lost. So in any case, B, C and D, they are not correct at all for car as a system. Correct answer will be A, simple application of Newton's first law of motion. Question number 3. What is the answer? Answer is D. Both of these statements are not correct. The first is description of sun synchronous orbit. Second is in any case not correct. Telecommunication satellites. Invariably तो किसी के लिए भी true नहीं होगा. Telecommunication satellites are invariably kept in geostationary orbit. That will also not be 100% accurate statement. There will be some telecommunication satellites which can be kept into LEO. But generally they will be kept into geostationary, geosynchronous orbit. Both of these are not correct. Answer is D. Satellite, small satellite launch vehicle. It can be used to launch multiple satellites in geostationary orbit. इसका इतना capacity नहीं है. Small satellite launch vehicle capacity is 500 kg, 500 km. It will reduce the turnaround time and cost for satellite launch. That was the precise purpose of small satellite launch vehicle. It has 2 solid strap-on, core liquid booster, cryogenic upper stage. Not at all true. 3 stages, solid fuel. Only 1 is correct. 2 only is the correct answer. Light detection and ranging. Remote sensing technology that uses laser beams to scan the environment. That is what LiDAR is. Generates its own transmit signal and can accurately determine distances. Now this is very important. LiDAR does not depend upon the prevailing light. I can have a device which is gathering light, and based on the gathering of light, it determines information, like our eyes. Our eyes are a device like that they gather light. Our eyes are not emitting its own light. But we can have devices which can emit its own light, and then they gather the reflected light. So LiDAR falls into the second category. All of the remote sensing satellites of ISRO are equipped with LiDAR. What about this? Why would that be? Like, that is a very random statement, that all satellites are only using LiDAR. In fact, hardly there are like 1 or 2 satellites which use LiDAR. ISRO relies a lot upon radar imaging, synthetic aperture radar, rather than LiDAR. So first and second, sorry, यहाँ पे and होना चाहिए. A is the correct answer. Question 6. अगर आपको कुछ भी नहीं पता है तो टोटल एनर्जी तो हमेशा कंजर्व होगा ना सिस्टम का. यहाँ पे कोई फ्रिक्शन जैसा फोर्स तो है नहीं. टोटल एनर्जी सिस्टम का कंजर्व तभी नहीं होगा when you have a force like friction, which is dissipative in nature, which leads to loss of energy into thermal energy, production of heat energy. Speed will not be same, because remember, in elliptical orbit you come very close to Earth and then you go far away from Earth. So whenever you are at perigee, your speed is going to increase. Whenever you are at apogee, your speed is going to decrease. Velocity, of course, will not be the same. That forget about the magnitude, even direction is changing. अगर मान लो circular orbit रहता तो speed constant होगा. In circular orbit, the speed part will be constant, but the velocity still will be changing. Now kinetic energy will also not be the same, because when you are at perigee, since you have higher speed, kinetic energy is half mv square. Now you have same mass, but v has increased. So kinetic energy has increased here. But total energy will without a doubt, total energy will be the same. That if your kinetic energy has increased, it also means that your potential energy has decreased. So that sum of kinetic energy plus potential energy, which is called total energy, that will always be the same. So in any case, even if I did not know other, for a system bound by gravitational forces, total energy will be conserved. This was an easy question. So answer 6 का जो होगा वो D होगा. 7th, So answer will be only 2, not only 1. Mass of Earth and distance from Earth, not dependent upon mass of satellite, which is counterintuitive to think. If you do not know the actual understanding of orbital motion, then you will think that mass of Earth will not play a role, but mass of Earth will play a role. We talked about this. That the gravitational pull is gmm by r square, and this is the centripetal force, so this should be mv square by r. But both sides I have small m. I remove small m, and immediately I know that my velocity will be gm by r. R is the distance from Earth, capital M is mass of Earth. So mass of Earth will decide. For example, same मास का ऑब्जेक्ट अगर सन के अराउंड रिवॉल्व करे सेम डिस्टेंस में, तो जो रिवॉल्यूशन पीरियड होगा मच फास्टर होगा. So mass of the heavier object will decide that how fast you are revolving. And by the way, how fast you are revolving will decide what is your time period of revolution. The time period is nothing but 2 pi r by v. ये होगा ना, 2 pi r is the distance you travel, circumference of this circle, and divided by speed here. So this will depend upon mass of Earth, and this will depend upon distance from Earth, but it will not depend upon mass of satellite. Answer will be only 2 here. Next, I guess, is easier. Remote sensing satellites, क्या होगा आंसर यहाँ पे? Monitoring of gas pipelines, yes. Monitoring of glacier lakes, yes. Study of mangrove ecosystem, yes. Horticulture assessment, yes. Vehicle tracking, fleet management, tele-education, satellite-aided search and rescue. So for vehicle tracking, fleet management, we use navigational satellites. For tele-education, we use communication satellites. For satellite-aided search and rescue, we use both communication and navigational satellite, but not remote sensing. Answer will be A here, only 4. Not all of them. Sorry? Gas pipelines हम monitor कर सकते हैं. We already do that. GAIL के जो gas pipelines है, they are monitored with the help of remote sensing satellites. Sorry? नहीं, LPG हम gas pipeline, घरों के gas pipeline की बात नहीं कर रहे थे. When we talked about gas pipeline, we are talking about like companies, GAIL के जो gas pipelines होंगे, IGL का जो gas pipeline हो, we are talking about that here. Sorry, you had a question. Somebody had a question. 1, 2, 3, 4. First 4 are correct, rest are not correct. What about Gagan? Now this is a tricky question. Answer will be all 3. Answer will be D here. Unmanned level crossing warning to driver in railways. Where that is located? जो गगन पूरा system है, देखो क्या है? Gagan system is navigational satellite which provides navigational information, but it also includes communication satellites. So it collects navigational data, it collects your GPS data, and then it provides information about that GPS data with the help of communication satellite. So first is true. This is in fact one of the serious issue country faces, that railway, हम railway को monitor कर सकते हैं गगन को, and जहाँ पे भी unmanned crossing होगा, we can develop an alert system. But all the unmanned crossings, we can know about its location and we can communicate about it with the help of Gagan infrastructure. Space weather studies, same thing. जो navigational satellites हैं, उनका जो distance, how much time it takes, is there any error in their signal processing, all of that will allow us to study about ionosphere or other type of objects in the sky. And forest survey, whenever we do forest survey, we use remote sensing satellite, but where that is located, जो location वाला part होगा, that will come from navigational services. So answer will be D here. In this particular question, answer will be D. 10 is easy, I guess. Only one, GLONASS, that is of Russia. QZSS is of Japan, Galileo is of Europe. Consider the following statements. यहाँ पे क्या होगा आंसर? Which one? नहीं, लास्ट भी कहाँ से सही है? थर्ड भी सही नहीं है. Answer is none here. So PSLV has only been used for launching satellites. The key word here is only. Only been used for launching satellites that are used for resource monitoring in polar orbits. PSLV has been used to launch satellites in geotransfer orbit also. I have talked about that. I am very sure that I talked about this. Don't talk in the class. Don't talk. Don't talk. Class ke baad. Okay? GSLV Mark II has been used only for launching communication satellites in geotransfer orbit. This is also not correct. In past, GSLV has been used for low Earth orbit also, particularly if your mass is heavy. And LVM-3 can be used for payload of 20,000 kg to be sent to low Earth orbit, only 8,000 kg. So third is also not correct. And ऐसा भी नहीं कि कुछ 8 और 9 था, अच्छा खासा difference था, 8 और 20 में बहुत difference है. So third statement is also not correct. Answer is none here. D will be the correct answer. 9,000 अगर होता तब भी जो इसरो का जो ऑफिशियल वेबसाइट है उसके लिए जो पैरामीटर विच वी यूज इट्स 600 किलोमीटर ऑफ पोलर ऑर्बिट. सो 9,000 kg it can launch, but that orbit has to be either less height or it has to be of some other inclination. Let's say 0 degree inclination, equatorial orbit. But such type of questions will not be asked, where there is a doubt of that you misinterpret a particular statement in a different way. But just in case, if the statement was that it can launch not 20, but had it been 9,000 or 10,000, even then I would have marked it wrong, because if you go to ISRO's official website, they mention 8,000 kg. And for me, I will use that as a benchmark. And it goes without saying that this 8,000 kg is for a particular distance, 600 kilometer of polar orbit. So if it is 400 kilometer, it can be more than 8,000 kg. 8,000 वो हो सकता है, but हम ऐसी चीज़ों पे UPSC नहीं पूछेगी. अगर difference होगा तो बहुत अच्छा खासा difference होगा. Question 12. This is one of the questions which you should eliminate and find the right answer. Answer will be EXPOSAT. EXPOSAT has two payloads. Both of them measure polarimeter, both of them measure polarization. Artemis is a lunar program of NASA. Nothing to do with any India's program. Aditya L1 mission does not have this. Chandrayaan 3, that of course is not correct. Question 13. All three, without a doubt, it should be very clear that question 13 ka answer will be all three. Question 14. I want more responses. What will be answer to question 14? Everybody should be very clear that answer will be D, that to achieve a stable orbit for long-term solar observation. बाकी चीजें गलत हैं. To ensure continuous telemetry contact with ground stations, to optimize solar panel efficiency and power generation, to avoid interference from Earth's magnetic field. Now, even though they can be partially correct, but the most appropriate option will be a last option, to achieve a stable orbit for long-term solar observation. Question 15. I want more responses here. Which of the following statements is correct? It is out of 4, 1 is correct. Such questions must be attempted. That I know that out of these 4 statements, 3 are incorrect, only 1 is correct. It is primarily designed for search for planets in habitable zone of other stars. That is not at all true. It can do that, but this is not designed for it. Just because I gave you a story, I told you one story, that it has found, that is only one example. It can do so many different things. It can find about formation of the earliest stars in the universe and earliest galaxies in the universe. It operates temperature close to absolute zero to maximize its sensitivity. That actually is true. I will explain this in next class. So remind me that why that second statement is true. Third, it is positioned in a LEO for easy access and maintenance. That is not true. I hope everybody is clear that L2 point pe hai. It is the first space telescope capable of directly imaging exoplanet. That is also not true. There are so many other telescopes. The best example will be Hubble. So you can eliminate other options, and B is the right answer, but I will explain why, what type of arrangement and why this arrangement. I will explain that in next class. 16. India became the second country to successfully land, not at all. India became the first country to land close to South Pole, yes. Mission has successfully analyzed lunar sample and has found huge reservoirs of helium-3, That's a made up statement. Nothing like this has happened. अगर ये होता तो बहुत बड़ा न्यूज़ होता. Helium 3 is actually quite useful, which I am going to discuss in the next class जब हम nuclear fusion पढ़ेंगे. Question 17. It may seem like a factual question, but it is not at all a factual question. In the first statement, there are so many wrong things. Exposat is India's first scientific observatory. It is not. Astrosat was the first scientific observatory. Weighing 1500 kg. Now चलो ये कौन याद रखता है? Although UPSC ने इस टाइप का भी क्वेश्चन पूछा था एक बार. Its mass is about 500 kg. That's not important. The last bit is very important. 1950 kilometer. If I try to send something in LEO, ideally I will go at 400, 500, 600 kilometer. At max 800, 900 kilometer. Just because the definition extends from 200 to 2000, I should tell you the most useful orbits are from 400 to 800 kilometer. So in any case, iska jo orbit hai, that is about 600 kilometer. 1950 is a very large value. So there are all the three things are wrong about Exposat. And second, should also be very clear that India has become the first country to launch a mission to observe X-ray sources in the universe. Now India is trying to do something in astronomy, but other agencies are quite capable of doing this. And NASA, for example, has launched X-ray sources, and other agencies also might have done it. So even second statement is not a factual statement. It should make logical sense that second statement is not correct. Second statement is incorrect. Answer is neither one nor two. Question 18. Both InSpace and Antrix are incorporated as government-owned company under Department of Space. Now, अगर InSpace को अगर हम NSIL लिख देते तो सही statement होता. So both New Space India Limited and Antrix Limited are companies incorporated, but InSpace is a regulatory body. Regulatory bodies are not incorporated as a company. RBI, SEBI, they are not incorporated as a company. But NTPC, that is incorporated as a company. Similarly, InSpace is a regulatory body. And accordingly, then second is also not correct, that both InSpace and Antrix generate their own revenue through satellite mission. Of course, Antrix will generate revenue, but InSpace का purpose ही नहीं है revenue generation का. InSpace का purpose क्या है? That जो private sector है, they do not find preferential treatment. It is a regulatory authority which aims to enhance private sector participation into space activity. Both of these statements are not correct. Answer is neither one nor two. अगर ये खाली Antrix होता, and InSpace को अगर हम NSIL से replace कर देते, New Space India Limited से, then both of these statements would have been correct. 19. Very lengthy question, but C is the most appropriate option here. So C is the correct answer. Locations in space where the combined gravitational force of two larger celestial bodies, like Earth and Sun, balance with centripetal force required for a smaller object to maintain a stable orbit with them. So C is the most appropriate option, even though it is a very lengthy question. Now 20, if you did not know, I am totally fine with that. Does anyone know what are Artemis Accords? What are Artemis Accords? Not International Space Station, in general outer space. Artemis, let me in fact, this also remind me about Artemis Accord and Artemis mission. I will discuss both of that in next class. Right now the answer will be a multilateral agreement establishing, no, not B, sorry, not A. C, a set of non-binding principles for peaceful and transparent civil space exploration. C is the correct answer. 21 is easy. Space debris. 22. Oort cloud, the most distant region of the solar system, that is true. That is where the most accepted theory here is that these are the origins of comets. So comets हमको कभी-कभी दिखते हैं, 100 साल में एक बार दिखते हैं. So they originate in Oort cloud and they find they travel in a very highly elliptical orbit around Sun. Kuiper belt is this entire region bit beyond Neptune. जो Neptune Pluto का जो region है, that is called Kuiper belt. So first is true, second is true. And asteroids that orbit with Jupiter around Sun, those are called Trojan asteroids. That is also true. Answer is all three here. 23. Out of 4, 1 is not correct. Option arrangement इस तरीके से है ना, that out of 4, 3 are correct, 1 is not correct. I just have to find the incorrect statement, and that is fourth statement. Solar winds and CMEs can't cause geomagnetic storm. Solar flares can cause powerful storms. That is not correct. The exact opposite will be true. A is the correct answer. A very similar question was asked by UPSC. I have just changed the options. यहाँ पे क्या होगा answer? Answer is A. Centrifugal force experienced by satellites is balanced by Earth's gravitational pull. So I've just changed the statements a little bit. I'm now analyzing this motion from the perspective of satellite. And satellite in its own frame of reference is at rest. And for objects to be at rest, the net force is 0. Now satellite is experiencing a gravitational pull towards Earth, so it should experience a force outside, and that force is centrifugal force. I told you that centrifugal force is a type of pseudo force which emerges when we analyze a motion in a frame of reference which in itself is accelerating. So the same statement would have also been that satellite receives necessary centripetal force from Earth's gravity. That statement will make sense for us. But the statement for the satellite will be that satellite ka jo gravitational pull hai, that is balanced by centrifugal force. So I can say the same thing in different frame of reference. So in this particular question, A is the correct answer. Jaise even Lagrange point ko leke, you will find a statement at some places that at Lagrange point, the attraction, the gravitational pull of two larger bodies balances the centrifugal force experienced by the third smaller object. So when that statement is made, this statement is made from the perspective of the third larger object. And the statement I have made you right, that the gravitational pull provides the necessary centripetal force, I have made that statement in our perspective. That in our perspective, a satellite or a spacecraft around Lagrange point finds a stable orbit because of gravitational pull of two larger objects. So I can make the same statement in different frame of reference. Last question, 25. The moon's rotational period on its axis and orbital period around Earth are equal. Discuss किया था मैंने, तो सही है. That both of that is about like 27.5 days, 28 days. And I also told you that this is because of tidal locking. So statement 1 and 2 both are correct. And statement 2 is actually explanation of statement 1. Whenever tidal locking happens, you find this both angular velocity to be same, answer will be A. If you did score more than 20, then I think you are doing fine. You're doing fine. So if you did score out of 50, more than 20, you are doing fine. But work more hard, revise, and read things by yourself. I will see you guys in the next class.